Download this code from codegive.com, link in the description below. Certainly. Instruction scheduling is a crucial optimization technique used in compilers to improve the performance of generated code by rearranging the order of instructions. This is particularly important in modern processors that have multiple execution units, allowing for increased parallelism. In this tutorial, we will cover the concepts of instruction scheduling and provide a code example to illustrate these concepts. Instruction scheduling overview. Instruction scheduling is the process of rearranging the sequence of instructions in a program to improve performance without changing the program's output. This is particularly useful in pipelined architectures, where certain instructions may have to wait for the results of previous instructions. Types of instruction scheduling. 1. Static scheduling. The compiler makes decisions about instruction ordering at compile time. This often involves analyzing the control flow and data dependencies between instructions. 2. Dynamic scheduling. The processor itself decides the order of instruction execution at runtime, typically using techniques like out-of-order execution. Key concepts. Data dependencies. These are constraints that dictate the order in which instructions must be executed. There are three main types. True dependency, read after write, occurs when an instruction depends on the result of a previous instruction. Anti-dependency, write after read, occurs when an instruction writes to a location that a previous instruction reads. Output dependency, write after write, occurs when two instructions write to the same location. Latency, the time it takes for an instruction to produce a result. Instruction scheduling aims to fill the gaps created by instruction latency. Resource conflicts, when multiple instructions require the same resource, example ALU, memory, at the same time, scheduling may be used to avoid conflicts. Instruction scheduling example. Let's consider a simple example in C that involves a series of arithmetic operations. We will look at how we can reorder these instructions for better performance. Original code. Analysis of dependencies. Y equals A asterisk B, instruction 2, can be executed independently of X equals A plus B, instruction 1. Z equals X asterisk Y, instruction 3, depends on both X and Y. Optimized code with instruction scheduling. To improve the performance, we can reorder the instructions to minimize idle time due to dependencies. In this case, the scheduling doesn't change the order of the actual written code but allows for a conceptual understanding of how we might rearrange execution to minimize stalls from waiting on dependencies. Conclusion. Instruction scheduling is a vital optimization technique that can significantly improve the performance of compiled programs. Understanding data dependencies and how to effectively rearrange instructions allows compilers to produce more efficient code. In practical applications, compilers like GCC and LLVM implement sophisticated algorithms for instruction scheduling, often employing techniques like loop unrolling, software pipelining, and others to optimize the execution of code on modern processors. Further reading. If you want to delve deeper into instruction scheduling, consider exploring the following topics. Compiler optimization techniques. Pipelining and superscalar architecture. Out-of-order execution in modern processors. Advanced data dependency analysis. This concludes our tutorial on instruction scheduling. If you have any more questions or need further examples, feel free to ask.